Good morning. I'm very happy to be here. My first time at JDK IO, and I'm very happy to see all of you here this morning. I know it's not easy to learn from the very beginning of the day. Today we're going to talk about GraalVM, which is the high-performance polyglot embeddable virtual machine developed by Oracle Labs. I myself am a developer advocate for the project GraalVM at Oracle Labs, which is, like, in general, if you're interested, Oracle Labs is the research and development facility department at Oracle. So their main goal is to do science, right? Research what is possible in the computer science and like what's possible in software engineering, and then consequently convert that accumulated research towards, well, hopefully successful projects for Oracle. You can find me on Twitter if you have any questions that you don't want to ask here, or if you come by any questions later. So before we go into any technical details, please do not base any foregoing business decisions based on the contents of this presentation. So with all that out of the way, let's talk about the runtimes, virtual machines, and all the fun stuff. GraalVM, it's a, as I said, it's a very large and ambitious and versatile project. It is a virtual machine capable of running or designed to be able to run all different languages. Typically, a virtual machine will be designed or supporting a certain language or a certain family of languages that all look alike. For example, normal JVM would work with any language that compiles to Java bytecode, but they are all kind of more or less similar. If you would diverge from that family of languages and go into a different realm, then, for example, your virtual machine could not be as efficient as at those. GraalVM tries to alleviate that, and we have made quite some progress with it. It's a long-standing academic research project. I think it's been in development for 7 years now, and just recently Oracle Labs the team figured that it is stable enough and mature enough to start converting that into an industrial project that we all can use and enjoy. So if you want to look into like the deep technical and academic, like actual proper details of what GraalVM is, what it offers, and how it operates, there is a bunch of academic papers. Well, since it's a research facility, that's what we do. We produce academic publications. You can start with this one, and from the citations for older papers, you can unravel the whole story of GraalVM. So you know that whatever I'm going to be telling you here is actually backed by the actual peer-reviewed academic research. You don't have to do that to make use of GraalVM or to actually benefit from GraalVM, but you can do that. So in one image, what GraalVM can do currently, it can run a magnitude of languages, including Java languages and Jvm languages, everything that compiles to bytecode. It uses OpenJDK as the base platform, so it runs on the time-proven, battle-tested software platform. Other languages that we currently are supporting are JavaScript, Python, Ruby, R, and there is a way to run native languages like C and C++, maybe some Rust, but it depends, on GraalVM as well. So this is the polyglot aspect. Why is this important? Because the world is polyglot. There are many languages. Every language comes with their own ecosystem of tools and libraries that you would like maybe to leverage in your application, because the cheapest code is the code that somebody else has written that you only need to glue together for your business case. And then GraalVM is embeddable, so it means that it has very different platforms as target where it can run. It can run on the JVM, it can run as a node process, it can run inside some databases embedded into native applications. It can be embedded in Java applications. You would like to extend your Java application with dynamic languages, and it can be compiled to a static not a static, to a native executable. So it's a very versatile project. It can do many things. If you want to roughly follow what it can do for you, we recently started publishing more content about what GraalVM does and how it does things. So you can check out medium.com/GraalVM or this particular blog post by Chris Seaton. I think he's the lead for the GraalVM's Ruby project. And we will do some demos of those things today, and we'll talk about how it works. From the architecture point of view, and this is what makes GraalVM so interesting. It's a layered architecture that enables more and more things towards supporting different languages. As the basis, we will have the platform, which is the normal JVM, an open JDK. So this is the Java virtual machine that is capable of executing Java Bit Code, and it can compile things just in time, right? And there is garbage collection going on, and there are all the components for the virtual machine that are necessary. From GraalVM project, there is the Graal compiler, which is a just-in-time compiler that can be plugged into the JVM using the thing called Jvm CI, the Jvm Compiler Interface. That interface was specifically developed to allow third-party implementation of the compilers to be plugged into the normal stock JDK JVM process, right? Using that interface, GraalVM project supplies this third-party compiler, which could be reasonably better than the default C2 compiler in Hotspot. And through that compiler, we can execute JVM languages. Everything that compiles to bytecode can be successfully executed on GraalVM. Jvm CI was introduced in Java 9. How many of you are running Java 9 and later in production? I salute you, brave gentlemen. So how many of you run Java 8? Okay, very cool. So currently, the easiest way to start benefiting from GraalVM is to run on Java 8. So we'll talk about this in a minute, but you're in a very good situation. There are ways to get benefits from that on later JDKs as well, but it's a little bit less prepackaged for you. So on top of that Graal compiler, now we can efficiently execute Java bytecode. But what we want to do, we want to execute all the languages, right? So what we need to do, we need to add some sort of level of indirection, right? Some support for other languages. So, and there is a thing called Truffle. And Truffle is a framework for implementing managed languages. What it gives you an API to build interpreters for the languages. So if you imagine how you typically define semantics of language, you would have an interpreter, you would parse your language program into something resembling an abstract syntax tree. So you will have a tree of nodes where every node is an operation, and then you would just iterate and go through the tree in some order and evaluate every node, and then this would be the simplest implementation of a programming language. It's kind of way easier to do that rather than to create a full-blown, efficient virtual machine runtime for any particular language. So this is an easier entry point for all the languages. So with Truffle framework, with this provided API for building those interpreters for abstract syntax trees, and Graal compiler, those two know about each other, and they can optimize execution of that tree to very efficient machine code. On top of the Truffle, on top of that framework, currently there are several efficient language implementations in different stages of completeness. JavaScript, and including the Node.js API, is probably the fullest, currently at around 99-ish% of compatibility with modern JavaScript and modern Node. I don't think the latest, because they released a new Node just a couple of weeks ago, but we will catch up fairly quickly. Ruby is the next one. compatibility is substantial. We are running tests on modules and libraries that we download from the ecosystem of those languages. So for JavaScript, we download NPM packages and run tests on those to make sure that we're compatible, not just with the spec, but we can actually run the software. Ruby gems, we test on our packages. Python implementation is very interesting, and to me personally, but currently it's making the first steps in this compatibility world. So it can run snippets of Python code, but it doesn't yet run fully like real world libraries and modules, mostly because of the native extensions. And then we have this very interesting bit. Because all those dynamic languages run native extensions, we would like to be able to run those as well, right? Because we are the VM to run all languages. So we developed a thing. On top of Truffle, we developed an Llvm interpreter. So Llvm is the compiler toolchain that offers you an intermediate representation of your program called Llvm Bit Code. This is kind of similar to Java bytecode, right? So it's a way simpler language than any of the high-level languages, and Llvm can offer optimizations on the bitcode level, right? We have the bitcode interpreter, so we can load the program that is represented by the bitcode, and we can execute that. Through that Llvm frontend for us, we can run all native programs that can be compiled to Llvm. So C, C++ programs, almost any modern language has an Llvm backend. We can run those with different levels of success, of course, because there could be very random things that people do in the native code. But it runs, and it can run native extensions to certain packages, gems, and modules through that. So this is what's supported. Now, if you're asking how it works that we can run actual interpreters for the abstract syntax trees and still be efficient, because it doesn't sound like it should be efficient. The answer is there are high-level optimizations that are applied to the program on the tree level before it gets to the bytecode level and starts applying optimizations in just-in-time compilation on the bytecode level. So imagine you have like a normal tree representing a program. When you start running that with Truffle and Graal, the tree doesn't have any information about what data passes through that. It just knows about what the nodes represent. But as you interpret that tree, it can collect the profile information, it collects the information about the types of the data that flows through that, and then it can specialize that tree. So it can have like a copy of a certain branch of the tree where the nodes are replaced with specific nodes targeting specific data types which will flow through that tree. So you will get a picture, something like that, where one subtree is expected to get only integer nodes. It can always de-optimize back into the interpreter if the profile information will change or if some other data will pass. But if your profile is consistent, profile of execution, then that tree can be further compiled into very efficient machine code, and you just smush nodes together, and then you compile whatever the operation that is into the bytecode and into the machine code. Now you're wondering, oh, how fast can it be in real life? And the answer is it's pretty fast, especially surprising because the normal JVM, for example, is such a highly optimized virtual machine. So we run the benchmarks against the best specialized competition, and this screenshot and those results are from the same paper I referenced before. You can see that we are mostly on par with the best specialized competition for all the languages. It is a goal for us to have the best, the fastest, the most high-performance virtual machine for all languages. So we should beat the competition, and we will get there, hopefully, sooner rather than later. But most probably we'll get there. If you look at the Java column on the left there, yeah, it's on the left to you, we are a little bit faster. This is mostly on the industry level benchmarks, Da Capo, SpecJDBs, and so on. It might be that your code, the code that you are writing, is a little bit different from the code that is written in those benchmarks. If you don't crunch numbers and do heavy math operations day to day, but you rather, I don't know, pass data, use streams API, maybe the performance boost will be much higher. Now, for other JVM languages, it's a little bit different story. Java programs and the normal C2 hotspot compiler, they have been growing up together for 20 years. So they intimately know about each other, right? Your Java programs are optimized to run well on C2, and C2 knows about the patterns that your normal Java programs produce, so they're a good match to each other. As soon as you deviate from that path a little bit, and you use a different programming language, the bytecode patterns could change, and then C2 might be not as excellent at optimizing those. So for example, for Scala programs, we typically get approximately 20, 25, 30% of performance boost, which is quite amazing if you think. For other languages which are not known to be super fast, the performance benefits are quite amazing. What is very surprising, and it was super surprising to me personally, is that we can run Llvm interpreted bit code at approximately 85–90% of the native speed. So the compiler compiles your Llvm bit code to native executable, right? It links everything together and it runs really fast, right? You know that if you want to run something fast, you have to rewrite in C. But through the interpreter, we can run it fairly fast. JavaScript as well. So compared to V8, we're a little bit behind, but 90% of the performance is actually quite a great result. So now I would like to start a couple of demos, but let's talk about how you can get it first, so you know what I'm demoing to you and what is the software that I'm using in the demo. It is GraalVM. It's an open source project. The main repository is on GitHub. It is available, all the components for that are available under the GPL2 plus the ClassPass exception license, which is the same license as OpenJDK. So whenever you can use OpenJDK, you can use GraalVM, the open source parts. The language implementations are typically what we have currently are with the, I think it's the universal permissive license. I advise you to check. I'm not a lawyer, but it is a more permissive license than GPL2, so you should be more safe with those as well. So you can download that, you can build your components, you can look at the source code. There are 2 editions of GraalVM that we currently offer. Oracle, we are providing the builds of GraalVM as well that you can just download. Those are built on top of JDK 8 currently. So there is a community edition which is built out of the components available in the open source. You can download that from GitHub. It is currently available for Linux. The reason for that is that we wanted to provide JDK 8 compatibility, and there is no Mac OS JDK 8 builds with Jvm CI enabled that we could use. So there are builds for Mac OS for Oracle JDK, so we could provide an enterprise edition of GraalVM for Mac OS, and you can download that as well freely from the Oracle Technology Network. This is the same place where you go to download Java. There is a license click-through that you say, where you say that you accept the license terms. It is free for development and evaluation use, which should be enough for anyone to experiment with it. So you can download both of them, or you can build your open source components yourself. The main difference between those two is that Enterprise Edition comes with additional compiler phases, so the performance of the Enterprise Edition will typically be better. At the same time, the community edition should be reasonable enough, and we're committed to make it fast, the community edition as well. So it's just, if you would like to then continue with getting more performance boost, you can look into maybe figuring out how to get the enterprise edition. I will show, so the community edition includes all the same things, and it is functionally equivalent to the enterprise edition, right? It can run all the same languages, it can run in all the same platforms, and it's available out there. So let's see what the next slide is. The base image, the distribution that you get from GitHub or from Oracle Technology Network, comes with JavaScript, with the Jvm languages, JavaScript, and Llvm Interpreter built in. They're pre-packaged in. If you want to install Ruby, Python, or R support, you need to use a command line utility, and you just say, oh, please install Ruby, and it goes and downloads a jar file from GitHub, and it installs that jar file into the correct places, and you get support for those languages as well. So, and if you are just running JDK 10, and you don't want to experiment with any downloads, there is a way to run the community edition of the compiler, because some snapshot has been brought into the OpenJDK project, so you can just unlock that with a couple of experimental options, and your JDK 10 will run with Graal compiler enabled. So if you run that, this is probably the easiest way to see how Graal compiler will perform on your code. That being said, let's stop talking about the slides, and let's try to run it and see what it gives you. So let me just cd into the GraalVM home. I would just want to show you. I downloaded the enterprise edition, and in late April, we released 1.0 RC1, communicating our desire to eventually release the proper 1.0 release. Now we got RC2 ready. Hopefully, just maybe a few more release candidates, builds that we will publish, and then we'll gather enough feedback from the community, and we will have enough confidence and enough motivation to do a proper release. So if you look at what you get in the package, it looks a lot like your normal JDK distribution. You can see in the bin directory where I have my executables, I have the normal Java, I have normal Javac, JavaP, all the rest. I also have GraalVM specific executables there. For example, JavaScript to run JavaScript, Llvm Interpreter, the npm executable, Ruby, R, and so on. And you can just run that. So if I do bin Ruby, anyone is a Ruby fan here? Who uses any languages that are not Java at work? JavaScript. Excellent, some people. C++. COBOL. You, sir, are my friend. So it's a normal like Ruby console. So for example, if we do sort, you can see that it actually sorts numbers, and it runs, and this is the particular Ruby executable bundled with the GraalVM. So you can get one download, and you can install those components, and you will be able to run like several different languages with the same kind of base image of the JDK that you are downloading. But let's not talk about that. Let's talk about high performance. I have a couple of demo applications here, and I would like to go through them. So the first one is, because performance is excellent and very interesting, it's a simple benchmark, right? What this benchmark does, it's a normal Java micro benchmark harness based benchmark. So this is how in the industry we evaluate performance of our Java applications. What it does, it just takes a bunch of integers, and what it does with that array of integers, it creates a stream, and then it applies several functions to the stream, so it iterates through the values and then multiplies and adds them, and then it reduces them into a sum. So it adds all the values together and returns that back to the out of the method. So we will benchmark this method, and I will run this. I hope it's all built, and I will first run this with no Graal compiler enabled. So if I just do run no Graal, you can see what I'm doing. I'm using the Java executable from GraalVM distribution, and I will disable the Jvm CI compiler. So inside the GraalVM, there is a normal open JDK build. So we are adding the Graal compiler into that build, but you can disable that, and then your code will run in a normal mode with normal interpreter C1, C2 compilers, just like any other Java executable, right? So if I now run this, I hope it runs fine. Really hope it runs fine. So it runs, it starts, it will warm up a little bit, do a couple of iterations. One thing that what we recently managed to do is, since JMH, Java Micro Benchmark Harness 1.21, GraalVM is the support, it's a recognized and supported virtual machine. So the harness makes, and it tries to make sure that whatever the virtual machine it is testing, it kind of follows the rules of good benchmarks. It inlines the code when it needs to inline, it respects the compiler hints, it respects the black hole semantics, and well, it does everything not to break the actual testing framework for the performance, right? So we run this, it takes 40 seconds, and you can see that the score, the time to run one iteration of that test method, is 183 nanoseconds per operation. So it's a decent score. Jvm is pretty good. So if I show you the run sh, it is the same thing. We are doing the same thing, except we don't specify that we would like to disable Jvm compiler. So on GraalVM, by default, this will run with Graal compiler enabled. And I will show you this run sh. Now it starts. I will not show you the numbers. Let's look at the benchmark. This is a fairly typical code that you and I can write daily, right? Since you said that you're writing Java 8 code, you use stream APIs, you pass data back and forth, right? So this is representative. I should tell you that you shouldn't you shouldn't take numbers from the benchmarks for granted. You should always try to figure out the interpretation, what has happened, why it has happened, and whether the benchmark actually is representative of the use cases that you are going to run in your application. But this is the code that you and I could write, right? Who agrees that? Who has written something similar in recent days? Excellent, almost everyone. So who thinks it will be faster than the stock JVM? A couple of people. Who thinks it will be on par or slower? Why would I show you benchmarks where our product is slower? No, it will be faster because it's a demo application, it's a benchmark. But now the question is how much faster? Who thinks it will be faster like 5%? 5% is a big deal. It's JVM. 10%? Nice. 50%. Twice as fast. Okay, let's see the numbers. It should have finished by now. So you can see now that with Graal compiler enabled, this benchmark ran, and one iteration of the method took 10 nanoseconds for operation. Let's scroll a little bit up. Without the Graal compiler, 183. With Graal compiler, 10. That's what? 10 to 20 not percent, 10 to 20 times increase in performance. This is where we all are like, wow, that's a lot. That is a lot. And the thing is, what is very exciting, this, of course, you will not be able to get 10 times increase on your normal applications, right? This is a synthetic benchmark. It's a small piece of code that Graal compiler can optimize extremely well, but they're showing that this is possible versus the JVM, which is a state-of-the-art virtual machine into which many very smart people put a lot of time to make it fast and get this result. This is absolutely ridiculous. So what this should tell you is that if you run Java, any kind of Java, you should try it. You should try either Community Edition, or you should try downloading the Enterprise Edition and to see what is possible on your code base, because just missing out on such a performance improvement would be a little bit sad. Now, I have another kind of, not a benchmark, but I want to show you one very cool performance optimization that Graal compiler does. So I have this code, and what it does, let me run this build run, because I will be talking about what it does while it runs. So we will run it, we will use the JVM compiler. So it will be running with GraalVM compiler. I hope it builds and runs. Come on, IntelliJ IDEA, don't fail me. So while it runs, come on, show me. Yeah, it runs. So what it does, it initializes a color plane, like a 3D array of colors, right? And for many iterations of the loops, it does some color manipulation, right? The normal code, so it initializes some color, and it does some mathematics, and it divides things, and it multiplies, and it writes color back into this 3D matrix of our colors. You can see that this code runs, and it starts a little bit slower, but then it optimizes itself into a fairly efficient code, right? So it runs quite fast. I will not run this without the Graal compiler, but I will do a change to this code just to show you a very cool thing. So now what we'll do, we will only write this color back into this, like our main memory, only if x is equal to y and y is equal to z. So we will only write it back. So we will do all the math, but we will only write it back to memory if we are on the main diagonal. So fairly rarely, right? So what should it do? It should do nothing to performance, right? Because we still do all the operations, and then we just not do this one particular assignment, which should be fairly fast. Now, if we run this, and I hope the difference will be pronounced, you have seen that was 500 milliseconds, right, at the end, 500 something. You can see with this code change, we start, and then we extremely fast, we go into the very small, really tiny numbers. So 6 milliseconds or 16 milliseconds compared to 500 before. Why it happens is because of the performance optimizations called practical escape analysis. So escape analysis also works in Hotspot and C2, but what Graal does, it figures out that those mathematical operations only make sense if we actually write the color back into our array there. So what it does essentially, it takes all these things and it pastes them, moves them into under our condition. So only for some of those colors it will actually execute math, and it will do that. So C2 currently cannot do that well, because even if it analyzes a program, it sees that the color escapes from this method and gets to the memory. So, but it cannot do this balancing of when it escapes or not. So C2 takes a more conservative approach, and Graal compiler shines and optimizes this code really well. So, and there are other optimizations that are quite aggressive inlining and polymorphic inlining, and that's all very interesting. But the takeaways here is that there are optimizations that it can apply to code that Java developers write daily, and we should all try it. Now, since we're here, I want to show you a different thing. I want to show you a polyglot application. This is currently, this project is a normal Spring application. It's a Spring Boot application, actually. So I will run it. Let me just Spring Array application run. Yep, it runs. Yeah, it starts. While it starts, let's see what it does. It's a typical Spring Boot application. So we just run that. We start the application, and we bind that to a certain port, and we can load that. Why this application is interesting is that we would like to use this particular R function inside our application. So normally you would have to go through the interop and foreign function interface or somehow tie things together. While GraalVM offers an SDK to write polyglot applications to, like, in a meaningful way to pass values between the languages and initializing context, I just want to show you that actually it's reasonably normal looking Java code that you can have. So the first thing you need to do, you need to create a context for the language, and we create the new context and we define it as a bean, the normal string bean. Then with that bean, what we do, we would like to get a plot function, which is we obtain by evaluating that R file. We evaluate that R file, and we say, since we know that it defines just one function, we say we would like this result as a function. And we expose that function as a bean. And we auto-wire that into this plot functional field. Think about that. This string bean is an R function from a different file. It's a totally different language, and it works surprisingly beautifully. If I just load this, hope it doesn't crash. Sometimes it crashes on me. Did it crash?
I don't think it crashed.
Oh, that's a shame. Oh, this is different. Let's try this, because this worked. So this is the same directory for the string R application. I think I have different versions of GraalVM installed, and in the particular that ID picked, there was no R support installed. So here it works, because this one I tested before the presentation. Let's see how it works. Come on, don't fail me second time in a row. It loads, and you can see that it works. You can see some data being printed into the log. What this is, so I want to show you what this application does. What it does, it just takes some values from the JVM world, right, some CPU load numbers, and it passes that to the R function. And then the R function generates this plot, because you know R is excellent at visualizing data. And then this plot is returned from our Spring application. Is it something that I see all of you doing every day? Probably not. But if you ever need a way to write a polyglot application or to enhance your Java application with dynamic languages, like offer some customizations with snippets of JavaScript or R or Python, then you can do that, and you can see that on this example, that the code looks fairly normal, right? I don't write any code inside strings. I can do that, but it's not necessary. And I can write my normal Java code, and I can write my normal R code, and I can pass values back and forth, and I can call Java types from my R or JavaScript, and it works beautifully. And currently, it presents this nice-looking graph to us. The important part here is that actually that library, the R script, which is very cool, it uses the ggplot2 package. If you don't know, it's probably the de facto plotting package in the R universe, and it also has dependencies on like half of the R packages in existence. Not half, but quite many. So this simple example actually shows some capabilities of GraalVM at running polyglot applications. That's awesome, right? Who's impressed? I'm very impressed. I'll stop this just to save the resources. Let's go back and see what else it can do. So if we talk about performance, you don't have to take just like, and you don't want to experiment with that yourself. What you can do, Twitter is one company that uses Graal compiler in production. They're running Scala microservices, and they're using Graal compiler, which I think they built from the open source repository themselves, and they plug that into their JDK Jvm processes. And Chris Tallinger, a very good engineer from the Twitter VM team, he has sessions at various conferences about how they use Graal compiler to speed up their microservices and save money on the cloud. Savings, of course, will depend on how much of the cloud resources you use. Twitter is a large company, so anything they can save translates into money. Oh, now, if you think about two projects, OpenJDK and GraalVM, There are different projects. There could be some confusion, but there are different projects run by different teams, and we have a little bit different vision from where GraalVM wants to be and where OpenJDK wants to be, right? So the collaboration between those is friendly, and we would like both of those to succeed. So, and OpenJDK, for example, picks Llvm Compiler as the Jvm CI compiler in Java 10 and further, right? So they use a piece of technology developed in GraalVM. GraalVM imports hotspot JDK, OpenJDK as a platform. So we would like both to succeed, but we're going into a little bit different directions. So they would like to be, I'm not sure what's the current OpenJDK official position and vision, but they need to care about stability, for example, a lot more than us, because they are powering, well, all existing Java applications in the world. So they would like to be very stable, very solid about design choices they make, and we can be more fast pacing, so to speak, because we're a much newer project. So, but there are two different things. So if you see somebody get confused about those, point them to my Twitter. I will be happy to explain. So, native images. One problem with typical Java application is that it's usually fairly slow to start up, right? We need to load the JVM, we need to warm up the JVM, load the classes from the runtime library. What GraalVM can do, it can compile your application, some Java applications. That's very important. Some Java applications can be compiled to the native executables. It will work with the memory management. It calls the whole idea of the Graal was that we would like that architecture to be embeddable. We would like the components of the virtual machine to be able to be provided from outside. So thread scheduling and garbage collection and code caches, those components of the virtual machine could be provided to GraalVM from the outside, and then GraalVM will still work at the same compiling magic. So there is an implementation of the small VM called Substrate Vm. It's written in Java, and it provides some implementation of garbage collection and all those necessary components. So, and that can be compiled to native code as well. So with those two, you can create a native image out of your Java application for way faster startup. And on top of that, not only you can embed your Java application, but also you can embed runtime libraries for dynamic languages. So currently JavaScript or Ruby, Python. And then those could be dynamically executed on top of that statically compiled, ahead of time compiled native image. I'm going to show you just, how much time do I have? I have some time. 7 minutes. Yes. Excellent. Let's be precise about that. I'll show you just a couple of demos because there is one more cool thing that I want you to see. So let me show you what? Let me show you file list. There is a thing called native list directory. So there is a normal Java class that doesn't do much. What we do, we create, this is a different Java class. I want to show you the normal list here. All those demos are available in the repository, so if you would like to follow them yourself, you can do that. So a normal Java class, what it does, it walks the file system, and for every file, it just finds if it's a regular file or not, and then it does some accounting on the file size, and then it prints some information about that. And we'll remove all the method handles because that should not be here. So what I can do with this in this application, what I can build a native image. Native image is the utility inside the GraalVM distribution, and what you do, you can pass a number of command line arguments and options, and you can pass your Java application, a class or a jar file or a collection of jar files with a class pass. And at the end, it will compile and it will give you a native executable. It will take a little bit of time, especially on machine running Docker and projecting and everything. So I've done that before. And ls ll list dir. This executable here, you can see it's native. It has just 5 megabytes takes 5 megabytes of space. And now if I do the running thing, I can do Java listdir and just running listdir itself, right? And I will time both of those. So if I run this, we can see, this is incorrect, wait. If I run this at least a couple of times, you can see that it walks the current path. It prints some information about the files. Also, you can see that the Java version of that Java listdir starts in approximately 200 milliseconds, which is reasonably fast for a small Java program. But also, the native executable starts way faster. You can see it doesn't take almost no time, and it's very fast. I can show you a different example of, say, compiling to native code a sample Java Kotlin application, because it is supported, because languages compiled to Jvm Bit Code can be, some of the programs in those languages can be compiled into a native image. This is very useful if you run your programs in a cloud, or if you have small programs where the startup is way more important than the peak performance execution. Because currently this implementation will be a little bit slower than your execution on the JVM in the JVM mode. You can apply the profile guided optimizations to make it faster, to collect the profile and pass it to the compilation, so it will be fast out of the box. But this is a little bit more complicated of an example. And also, you should note that there are limitations to this. The most notable is that we require the closed universe assumption. We require all the classes being known at the image generation phase. So you cannot dynamically load classes while your application isn't running. There are also other differences between things, but the important thing about the native images is that there are a number of applications, real-world applications that can be compiled. Some native applications, some vertex applications, some small applications using small libraries for doing and issuing and serving HTTP requests. Some closure programs. For some reason, closure people love us. And I have 2 minutes, and I want to show you a very interesting example, and I will do that until I will be here until they will kick me out. So, but polite. So one of the goals of the GraalVM was to be able to run in native applications, namely the database. It would be amazing if you could run random languages inside your database. If you don't want to write your stored procedures in PL SQL, you have an option now to run it in JavaScript. You don't have to do that, but it is possible. Now, there are, for example, experimental builds of Oracle database available that you can download, and you can experiment with this. I have this one started in my Docker container, and I will do this, create the thing, and I will just copy random things because I don't think I will be able to write it fast enough myself. So we'll create a directory inside my Docker container here, and this Docker container runs a database. What I will do now, I will just create a normal package, and I will download random npm module. It's not random, but it's a module called validator. You can see that it's a normal module. People are using that, 1 million a week. What it can do, it can validate strings to be or not be something, right? Now, with this module installed, and with the types for that module installed, because database is strongly typed thing, I can install that module into my database. And then it will export the functions from that module, exported functions, as stored procedures. And after that, I can do this magnificent line of code, which I should be able to do. I start the SQL plus the console to execute my SQL, and I can do now very interesting things. This is incorrect. I can use the validator functions to validate emails, and you can see this is an email. And for example, if I don't have the proper email, no tricks. This is actual JavaScript code running in the database. You can get 0 because it's not an email. So the whole power of NPM is available to you inside the database. Currently, experimental builds of Oracle database, MySQL plugin to support this is coming. All in all, I'm out of time. What I would like to say that there are a bunch of resources on that you can look further. If you have any questions, come talk to me, find me online, find the team online. We would be very happy if you experiment with GraalVM, and I hope you will be happy to experiment with that as well. Here are, for example, how you can do that. Thank you.